Alright, starting off with galvanic cells. When we talk about electrochemistry, we talk about galvanic cells, right? So when we talk about galvanic cells or electrochemistry is basically the conversion of chemical energy into electrical energy, so basically electrons. A galvanic or a voltaic cell we say is spontaneous, or the new word is it's favored, thermodynamically favored. So what does that mean if it's thermodynamically favored? It means it happens. It means you're going to produce a lot of products, so your K is going to be greater than 1. And if your K is greater than 1 and you know what's going to happen, it's going to be spontaneous. That means if it's thermodynamically favored, my delta G is going to be negative, and my E cell that I'll end up calculating is going to be positive. So those are things I definitely need to know about a galvanic or voltaic cell. So like if you know something has a very large K and it's a voltaic cell, you know it's got to be spontaneous, and you know the E cell value has to be positive. Whereas an electrolytic cell, you have to apply electric current to drive a non-spontaneous reaction. So in that case, if it's non-spontaneous, it means it's going to be a reactant-favored reaction. That means when you compare K, KQ is going to be less than 1. Your delta G value is going to be positive, and your E cell value is going to be negative, since it's going to be non-spontaneous. So that's kind of linking all those ideas together. The idea of equilibrium, thermodynamics, and electrochemistry. That's kind of what we're trying to do here. We talked about this before. Oxidation is a loss of electrons. It's an increase in your oxidation number. So for example, magnesium elementally has a oxidation number of 0 here, 0 here. Magnesium is 2 plus here, oxygen is 2 minus there. So magnesium goes from 2 plus to 0 to 2 plus, which is an oxidation. Oxygen goes from 0 to 2 minus, and that's a reduction. So that is definitely a redox reaction. Here, if you look, magnesium is 2 plus, O is 2 minus, H is 0, Mg is 0, H is plus 1, O is 2 minus. You notice here, Mg is actually being reduced because its oxidation number is decreasing. The reason why decreasing its oxidation number is because it's gaining electrons. So we track the electrons, but really we assign oxidation numbers to figure out which to make sure it's a redox reaction. When we go to balance redox reactions, we use the half reaction method. That's eating old hibachi chicken cold sucks. So you start out with the two half reactions. So in this case, Fe2 plus to Fe3 plus, that's going to be my oxidation. And then chromium goes from 6 over here to 3 plus over here. Because remember, like here, the reason why chromium is 6 is the overall charge on this thing is equal to -2. We know that oxygen's 2 minus, so 2 minus times 7 is -14. The thing that's going to cancel it out is you're going to have a positive 12 when you add them together, which means 2 chromiums. Each chromium would have a oxidation number of 6. So when we go to do the half reaction method, I write out the two half reactions, so Fe2 plus to Fe3 plus. At this point, there's no other elements that checks. There's no oxygen. There's no H, so then we just balance charge. This side is 2 plus, this side is 3 plus, so we lower the high side by adding an electron. Then when we go to the second half reaction, Cr2O7, 2 minus, 2 arrow, Cr3 plus. First thing we do is we start with other elements. In this case, chromium is 2 on this side, so I need to put a 2 on that side to balance. Done. Old stands for balancing oxygen. I have 7 oxygens right here, 0 here, so I'm going to add 7 waters to balance out the oxygen. Hibachi stands for balancing the H's. At this point right here, I have 14 H's, so I come over to this side and I add 14 H plus. Boom. Chicken stands for balancing charge. So when I go to balance charge on this overall side, this has a 0 charge right here, nothing. So this is nothing. Coefficient times the charge, so 2 times 3 is going to be positive 6 on this side. If I look here, 14 plus times a positive 1 is 14, but this is going to be 1 times a -2, so the overall charge on this side, -2 plus a 14 is going to be 12, which means I need to add 6 electrons to this side. Now, what's critical in a redox reaction is the electrons have to cancel. At this point, I have 1 there and 6 there. So I'm going to multiply the top by 6, 6, 6, 6. Then what happens is my electrons cancel. The N number we use in electrochemistry is equal to the number of moles that is transferred in a reaction. That's going to be 6 in this case. And then if there's anything else common to both sides, I would cancel it. We just used the cold stands for lowest common multiplier, which was 6. And then basically everything tetrases down. So you would end up with 14H plus 6Fe2 plus Cr2O7 2 minus 6Fe3 plus 2Cr3 plus 7 waters. If there's something that's the same on both sides, like the waters, for example, in this case they're not, but if you had waters on both sides, you could simplify by subtracting the smaller one from the larger one. Okay? Next is a galvanic cell. We talked about that. Here's an example of a galvanic cell with zinc and copper. If you look basically on your sheet, you have zinc and copper. If you look at zinc as an oxidation or a reduction reaction, Zn2 plus 2 electrons, you have it on your paper, Zn is a solid, that's equal to negative 0.76. Copper's reduction value is equal to positive 3.4 volts. When it says it's galvanic or voltaic, that means it's got to be spontaneous. So on the AP exam, they're going to provide you two numbers. You basically flip the smaller one. So see how this is negative 0.76. So I'm going to take this reaction. As you see it here, it's been flipped. When I flip it, I just change the sign. So then it becomes positive 76 volts. So then what happens, I have my anode, which is my oxidation. If you remember car audio, anode is oxidation. My cathode is my reduction, and I'll tell you where those are in the electrochemical cell. This is the anode, this is the cathode. The first thing that happens is I have checked my electrons cancel, so my N number is going to be 2. Next thing is, I total the overall reaction. I get Zn as a solid, copper 2 plus, Zn2 plus, copper is a solid. To find my E cell value, my E cell potential, all I do is add the two numbers together. So when I add these together, I get 1.10 volts. I knew it was already spontaneous because it said it was galvanic. My E cell is positive. That means my KEQ is greater than 1. That also means that my delta G is negative. It's thermodynamically favorable. So remember, car audio stands for cathode is where your reduction occurs. Anode is where your oxidation occurs. Now, here they used to give you a reduction table. Remember, the higher you are up on the reduction table, the more likely you are to gain electrons, basically, because a reduction is a gain of electrons. The farther you're down, or the more negative your value, your reduction value, the more likely you are to lose electrons. So you want to keep that in mind. That's an easy way to kind of think about it. Here is the electrochemical cell I showed you earlier. The zinc anode, remember, the anode was the oxidation. So key things you need to know, if you look right here, when you look at the electrochemical cell, anode. Zinc is the anode from what we looked at before. We know oxidation occurs there. That's car audio, right? Electrons are produced at the anode, so zinc basically kicks off its electrons, 2 electrons. The electrons always flow from anode to cathode. Anions migrate towards it in the salt bridge, so the anions always migrate towards the anode, hence the name. So anions, this shows a porous disk, but usually you'll have a little salt bridge right here, and the anions would go this direction, cations would go this direction. Usually we use something like K plus, NO3 minus. That's typically what you use in a salt bridge, something that's going to be always soluble. And the anode is associated with a negative sign. The cathode is where reduction occurs, car, this is audio. Electrons are consumed, so electrons travel this way, they're consumed, and the electrons are basically used to change copper 2 plus into copper as a solid. Cations migrate towards there, and it has a positive sign associated with it. A salt bridge, the purpose of the salt bridge is it completes the electrical circuit. It will have something that's called an inert electrolyte. Basically means its ions will not react with anything else. So it has to be basically always soluble. That's the key thing. Here's an example what you'll see on the AP exam. They'll say, oh, look, here's a voltaic, make a voltaic cell out of these two. They're not going to give you a table anymore, but they'll provide you these two values. The way it works is, since it says it's voltaic, I flip the more negative. So I'm going to take this one, which is at negative 1.18, which means it's going to be farther down the reduction table, so this is more likely to be oxidized. I change this into Mn as a solid, flip over Mn2 plus 2 electrons, and then positive 1.18 volts. At this point, my electrons don't cancel, so I multiply this by 2. This is going to be 2, 6, 2. I don't touch the voltage. I multiply this by 3. So this is 3, this is 6. Again, I don't touch the voltage at the end. My electron, or my N number, is going to be 6. So my electrons are canceling right here. Bam. To do the E cell, I add the two numbers together. I get 0.44. I knew from the fact that it was voltaic, it was going to be spontaneous, so I knew my E cell value was positive. The other thing they do is if they give you the equation, you make it match the equation. You don't always blindly just flip it. So if they give you the equation, it means chances are it probably won't be spontaneous. So if I look, they gave me the equation right here. Fe2 plus has to be on the left, so that means Fe2 plus in this one, I keep that there. If you notice, Sn is a solid, there's Sn is a solid, which means this one has to be flipped. So when I go to flip this one, I basically do this. I'm going to change this to positive 0.13 volts. So then I end up with Sn arrow Sn2 plus 2 electrons. Ultimately, when I go to find the E cell value, when I add it together, I get negative 0.30 volts. That means it's non-spontaneous or non-favorable. Non-favorable reaction, which means my delta G is going to be positive, my KEQ would be less than 1. So those are key things you want to think about. If you're given the equation, make it match. All right. A lot of times I'll ask you to calculate Gibbs free energy. This equation's in your booklet, so it's not that big of a deal. N numbers from the moles of electrons that cancel. So if you go over here, in this case, my N number would be 6. So I would come over here in the equation. I would just basically negative 6. My E cell value from the one I just looked at was 0.44 volts. And, oops, I'm going to move that over. I put that in the wrong spot. So I'll move that. Whoops, there's not. And then finally, if I look right here, actually Faraday's constant, which is listed in your book, don't have to memorize it, 96,500. My E cell value from that example was 0.44 positive. So ultimately this is going to kick out delta G. So I can go from E cell to delta G. My E cell's positive. I know my delta G is going to be negative because of that. When I multiply it all the way through, I'm going to get delta G in joules. I could divide by 1,000 to kick it into kilojoules. That's easy enough. Electrolysis. When we do electrolysis, you're adding an outside power source. So the key thing that they'll ask you in electrolysis reactions, they'll ask you to find out how much is produced. A lot of times in electrolysis, you're adding electrons to plate of metal, basically, is what you're doing, like gold in this case. So the equation I told you before, and you should have in your notes, is it N phi. That's basically what you're solving for. I stands for current, which is going to be in amps. T stands for time, which is going to be in seconds. N is usually what you're solving for because that'll give you moles of the product that you want. Moles of the product. F is Faraday's constant, which is 96,500. E is represented by the number of electrons required to reduce, because if you have Au3+, it means I have to add 3 electrons to get it to Au as a solid. So that's basically where the E comes from. So basically, if I go to rearrange this 1 hour, 1 hour is I need it in seconds, so that's going to be equal to 3,600 seconds right there. My current, they tell me, is 1.5 amps. I plug that in for I. Then what happens is I take F and E divided underneath, so 96,500. The number of electrons that I am reducing it by is 3 from the reduction reaction. So 3 electrons. I do the math and I'm going to get moles of Au or gold. If they ask me for grams like they did that, in this case, once I find the moles, I just multiply times the molar mass of gold, which is 197. So you do the math, calculate this out, you get N or moles of Au, multiply it times the molar mass, and you're good to go. All right. Last key thing that happens in electrochemistry, they do it a lot on the exam, is standard conditions for electrochemical cells are 1 molar concentrations of reactant and product ions. Remember, in equilibria, we don't focus on the solids. The solids don't do us any good. So then when they ask about Le Chat, they ask about basically what happens to the E cell value when you add or remove something. It's Le Chattier is basically what's happening. If I add or increase the amount of aluminum ions, I shove the reaction this way. If I make more products, when my products increase, my E cell increases. So if products go up, my E cell potential is going to go up. So this way, if I add it here, shift it this way, my voltage would go up. It would increase. What happens if I do something else? So what happens if I increase the amount of magnesium ions? What that does is cause the shift this direction, so I'm going to get more reactants and less products. So what's going to happen is my voltage is going to decrease because my E cell value basically is going to drop, because what's going to happen is I'm going to shift this direction. I'm going to have more reactants and products, so my voltage will decrease over because of the Le Chatelier, the shift to the right, or shift to the left, excuse me, shift to the left. So these are the key things you need to know for electrochemistry and be able to do. All right, have a good weekend. I will see you on Monday. Keep in mind, there's basically, when this weekend's over, you have 7 days. Your goal is to pick up 10 questions. If you study a little bit every night, think about it this way. If you pick up two topics, learn 2 things each night, by the end of the week, by May 5th, you will be exactly where you want to be for the exam. All right, have a good evening.